This is an overview of the controller inside the robot leg. It has 3 different activities. There's stair ascent, stair descent, and walking. Then all of those go through the standing sitting controller so that this will avoid it picking the wrong activity. So for safety reasons, if you want to climb, you have to stop and then climb, and then stop and then walk, and then stop and then go downstairs, for example, like that. And then the transition time is roughly 1 second, so it's not a big noticeable difference, but we have the pause so that it'll stiffen the leg up, be real stable, and then they can start their next activity. The equation for controlling the motors is here. It acts like a virtual spring and damper. So there's a spring constant, joint angle, desired joint angle, and then damping times velocity. So this is resistance, this is like a spring. And then we transfer that into current controls to send to the motors. The Stair Ascent controller is the one that I developed, and it has 4 states. 2 of them are active, 2 of them are passive. So in the active state, it straightens the leg. So the prosthesis here is the dashed line. It'll straighten the knee to raise a person up over the stair. Then once the knee is straight, it goes into a passive state called rollover, where it just is all stiff, waiting for the person to put their good leg on the next stair. Once their good leg is on the next stair, and we can tell that by knowing once enough force is off of the prosthesis, then it'll go into step. So the knee bends, the ankle flexes, and they can raise their foot up. This is a trajectory controlled state. So rather than just trying to snap up the knee to one specific value, it will control the joints through a series of values so that it actually is making a step. And then once it's completed its trajectory, it hangs out here in the bent state. This is passive. And the knee and ankle have a little bit of resistance, but not too much, to allow the person to bend the knee and the ankle and get their weight over it. So once their weight's over it, it cycles all the way back through. You can enter using into state 2. So it'll go into that stepping state. And the amputee does that by holding his prosthesis out kind of behind him. And then it recognizes, okay, he's trying to climb stairs, bends the knee and the ankle so he can step it on the step. And then if he wants to stop climbing, he just has to stand on it, and eventually it'll go out. I had to test 3 amputees. So I recruited 21 actually. And when they learned that they needed to climb 10,000 stairs each, they were not so excited. But 3 people did end up finishing. Many of them were unavailable. Some of them were too short, too clumsy, too heavy, or just not able to physically climb stairs. Since stair climbing is like with both their legs, that's a motion that they haven't done in years, then like to do that with a robot to you where you can't actually feel your feet is pretty scary for a lot of people. So that's why it took climbing so many stairs for them to get used to it, and for me to tune the controller to figure out what values do I need to put in for the coefficients that it will make their gait look like normal human gait. So these are the 3 subjects who stuck with me through the whole climbing the mountain. I'm super grateful to these guys for helping me to graduate. The equipment that I had to test with, and this is because, as I learned, unfortunately, research is not necessarily about making the world a better place. It is about contributing to scientific theory. So my professor basically told me, you need to prove that our robot leg can make gait easier and more natural for amputees. So to prove that, I had to test easier by measuring the oxygen and carbon dioxide that they breathe in and out and calculating energy consumption. Then more natural, using the data from the joint encoders and motors and stuff like that to see if the gait looks like healthy gait. The rules I had to define for people: no energy drinks, no cocaine, one step at a time. Consuming powerful stimulants can mess up your metabolics and your heart rate because you're breathing a lot differently than you normally would. And then climbing multiple steps, or like if you skip stairs, which some of them would try to do to go faster, then that creates unequal comparisons between trials. But with these rules, we were able to get some good results. This is a stair ascent controller in action. So you can see when the knee straightens and then the joints bend, and it goes through the cycle. It takes a lot to get the knee and the ankle synchronized and pushing at the right times. Depending on how tall the person is or how much they weigh, then we have to adjust a lot of those controller parameters, the threshold, the coefficients in the equations to figure out what will give this person the most normal gait. But once they get climbing with it, they really like it. It makes stair climbing a lot faster, and they like being able to do an activity that they haven't been able to do in years.